Hello and welcome to Lecture 16 of Math 2R03. In today's lecture, we're going to look at Section 5.A of the textbook on invariant subspaces. So this will actually be the first of two lectures on this topic, so part one. And the motivation or kind of the starting point for today's lecture is kind of going back to some of the material we learned in Math 1B03, where we learned about an eigenvalues and eigenvectors. So I've actually written the definition here just to remind you that when you had an n by n matrix, lambda is an eigenvalue if there exists a non-zero vector v such that when you multiplied the vector v by the matrix A, you got a scalar multiple of the vector that you started with. So today, what we want to do is we want to extend this definition beyond matrices. And in particular, if you're getting used to kind of our new way of thinking, when you're doing a matrix A and you're thinking of the matrix A times V, really what you're doing is you're looking at a linear map. And so that's what we want to do in today's lecture is think about what would this definition mean if we were to think of everything in terms of linear maps. Okay. So our starting point is going to be talking about what an invariant subspace is, and then we'll get into the generalization of an eigenvalue for a linear map or a linear operator. So make myself disappear so we have some more room on the screen. So the first thing I want to talk about is what is an invariant subspace. So first of all, I want to do some notation here. The notation will come in throughout the course, and we don't really use it too much today, but we'll see it in the future. So here, suppose that you have some function between vector spaces, and this definition actually doesn't even necessarily require that V and W be vector spaces. It would actually apply to any two sets V and W. Suppose that we have a function from V to W, and we have that U is some subset of V. Then T with a line with a subscript U at the bottom is called the restriction of T to U. And what it is it's a new function. Okay, let me write it out. So it's a new function that goes from the set U to the set W, where when we input a value into this function, it's the same thing as the value that we would have got if we stuck it into the function U. So really what we were just doing, okay, is you're just restricting the domain to the subset U, and we ignore the elements in the rest of the space. So you ignore the elements in the complement, V minus U. So whenever you have a function, if you take a subset, you can make a new function from that subset to the codomain just by ignoring some of the elements. Okay, so we're ignoring the elements in V minus U. Okay, so that's good to know. And the other thing that we want to define in this first part is what it means for a subspace to be invariant under a linear map. Okay, so here we have T, it's a linear map, or because we're going from V to itself, remember we would call this a linear operator. And a subspace of U is invariant under T if TU is an element of U for all vectors U in U. Okay. Now, it takes a second here to parse what this definition is. So let me maybe draw a picture of what's happening, and that might help you understand what it means for a subspace to be invariant. So we have two vectors, or we have the vector space V, and we have the same vector space over here on the other side. And T is a linear operator, right? So T is a linear operator, so it's a function that maps from V to V. And let's say inside of it is some sort of subspace U. Okay, so it's the same subspace on the same side, right? So these are copies of each other. And a subspace is going to be invariant if everything inside of U, when you stick it into your function, you end back up inside of U. Okay, so every element every element of U is mapped back into U. Okay, so if you were in U to begin with, after you're stuck into the function t, you get back inside of U. Okay, so that's what a kind of one way to think about what an invariant subspace is. And for any linear operator, there are examples of invariant subspaces. So let me just kind of give you some of them. Okay, so if you think of the subspace containing just 0, that's going to be an invariant subspace. A bigger set would actually be the null space of T is also going to be an invariant subspace of T. And then we have kind of the bigger ones, V and the range of T are also going to be invariant subspaces. So the V one is quite easy to see that it's invariant because if we go up to the map or this picture, the U is all of V. So it's just saying that if you take a function element in V and stick it into T, do you end up back in V? Well, you sure do. Okay. And the 0 one is saying that if you took the 0 vector over here, does it end up back into the 0 subspace on this side? Well, yes, that's true because every linear operator maps 0 to 0. And just let me show you a quick proof for why 2 is true. So let's say I take an element U in the null space of T. Then by definition, TU is equal to 0. Right? But the vector 0 is also an element of the null space of T. So we have that TU belongs to the null space of T. So anything that we start with, we took any vector inside of the null space, after we apply the linear operator, we end up back into the same space. So before we pause and talk about eigenvalues and eigenvectors, let me just introduce two fundamental questions that are going to kind of drive what we're going to see in this course for the next couple lectures. So two fundamental questions are, does T have any invariant subspaces? So if I hand you an arbitrary linear operator, does it have any invariant subspaces? Well, on the previous page, I just showed you that it has to have some, but can we say that there are others, okay? If you have something unique about T, do you get some unique invariant subspaces? And secondly is, can we find subspaces U1 up to UT inside of V such that you can actually break V into a direct sum of these subspaces and T is invariant on each subspace UI. Okay, so part B is a kind of a pretty complicated question, but what it's saying is once you have a linear operator, you're looking for invariant subspaces, and you want hopefully that if you look for all the invariant subspaces and you want to say, can I glue them back together, and does that actually tell me something about my vector space V? So keep these questions in the back of your mind. We won't obviously answer them in today's lecture, but it's something that kind of motivates what we look at in chapter 5 and then when we get to chapter 8. So I'll see you in part 2.